Yeah, and then we distinguish between real concept drift and virtual concept drift if we have a look at PXI. Well, PXI, the probability of observing the observation xi, that may change. Yeah, and if that also impacts a change of the posteriori probability, so our decision actually, then we are talking about a real concept drift. Yeah, so it refers to a change of the probability that we pick we pick y given xi, yeah, if that happens, we are talking about real concept drift. If the probability of a given observation changes without affecting the decision actually, yeah, so this is the probability we take for decision once again. So if the probability for an observation xi changes without affecting the decision, we are talking about a virtual concept drift, not a real concept drift. And you see here an example. So this is the original data, and yeah, if we have a look here, then we see that yeah, the decision boundary changes because the posteriority Wahrscheinlichkeit probability changes, obviously. Yeah, here px changes because well, the probability that we observe something here, which we observed here, so this one has been observed at that time slot. Now at that time slot we do not observe this one here, so the probability of this observation changes from 100% to 0%, say, yeah, simply speaking. Yeah, but the decision boundary does not change actually. Yeah, so the posterior probability does not change. Yeah, so this is a virtual concept drift. Even we observe different data, the decision boundary remains the same. Basically, that's the intuitive saying for that. Yeah, and we also distinguish gradual changes, which we call the drift, from abrupt changes. So changes all of a sudden, which we call, or the community calls then a shift. So a drift is a gradual changes, or are gradual changes. A shift involves more harsh or more abrupt changes here. Yeah, and then we have seen that before. Yeah, as data evolve over time, the classifier should of course update to this evolution of the data, especially by incorporating new data and forgetting obsolete data. So we saw this picture before. So from time slot T1, where we have this decision boundary here, we get to time slot T3 with a completely, not a completely different, but a considerably different decision boundary. And of course, we want to adapt to these new changes according to the decision boundary, or related to the decision boundary, by incorporating new data and possibly also forgetting about old data, obsolete data. Yeah, that's very important. So we typically need a kind of aging mechanism here. Yeah, and then once again, this distinction, the batch classification problem given a finite training set where y is the class label, find a function to predict the class label for unseen data from the training set. Yeah, and now in the stream classification problem, we typically deal with an infinite sequence of pairs of training data, and we want to find again a function that can predict the class label for unseen instances. Yeah, here the footnote says, okay, aging models are not so important for classification because in that case, well, we still can somehow manually yeah, choose training or the chunks or the period of time we use for training. Yeah? And the assumption here in the data stream classification problem is a little bit unrealistic, but okay, that's how it is. The label y of x is not available during the prediction time, but it is available shortly, in parentheses, after that prediction time for the model update. Yeah, so it's a kind of weird assumption that well, we predict the label of the next object or observation coming from the stream, and shortly after we predicted it, it is available for training or updating the new model. Yeah. So and this shortly, of course, is a little bit a dehnbarer Begriff, but yeah, it somehow suggests that yeah, things are predicted, and then all of a sudden an expert confirms the prediction or changes the prediction, and then we have this observation available also for training or model update. Yeah, so somehow is the image of some poor guy who watches the stream and takes the label of the class and confirms the label. Yeah, in real time, which is somehow a little bit awkward. But anyway, yeah, that's how people view the whole thing in order to do the model update with recent data, actually. Yeah. Okay, so then we have to talk about the question how to train actually or retrain the model. So what kind of data should we use? Yeah, and how to do that also technically. So there are different approaches. Typically, every approach proposes to use different chunks of the data of the stream, and here are the different approaches. So the first approach is quite simple. We train and retrain a classifier at regular intervals, the so-called chunks. Yeah, and the window size can be fixed or adaptive. Yeah, so after a given number of chunks, each chunk represents a given number of observations from the stream. After a given number of chunks, we retrain the classifier, you know, from scratch or whatever, which is somehow a little bit like the batch scenario. Yeah. The second approach is we train classifiers for several window sizes, several chunks. Yeah. So we have m chunks of equal size, and we train a classifier on the most recent h minus m chunks for m ranging from 1 to m, for h, sorry, ranging from 1 to m. Yeah. So let's say we have this is the m number of chunks. Yeah, and we train a classifier for the first chunk, or for the most recent chunk, for the last two recent chunks, for the three recent chunks, for the 4 recent chunks, and so on and so on. Yeah, and then we test the performance on the newest chunk, which is the evaluation set. So this is the training set somehow, and this is, or those chunks make up different training sets, and this is the evaluation set. Yeah, and then we test the performance on the evaluation set, the newest chunk, and we use the best classifier actually. You know? And the third approach is that we use basically an ensemble of K classifiers which are trained from sequential chunks. Yeah? And for a new chunk, XL, we train a new classifier using this chunk XL as training data, and we test all previously trained classifiers on this new chunk as test data, and we set their weight to the maximum of the mean square error of a random classifier and minus the mean square error of this classifier we test in that case, and 0. Yeah. So m as mean square error of a random classifier is just yeah, the error of a random classifier. So it's the probability of each class times 1 minus the probability of each class. Since it's mean squared error, it's squared. The error of each class is squared and then summed up. Yeah. So this is the error of a random classifier, and the error of classifier I is 1 times the size of the chunk we used for training this classifier, and then we have the probability for each class that the classifier picks this particular class. Yeah, and so we can test all the classifiers we already have, and then we keep the best K classifiers. Yeah? So we always have K classifiers, the potentially K best classifiers from the most recent chunk, and for the classification we use a weighted average of the ensembles we had. Yeah? So those are basically the three different approaches using chunks for training and for training actually and evaluation.